Hello there, welcome back to 10-Minute Physics. Today, in 10 minutes or less, we will take a look at the impulse change in momentum formula. We've already looked a little bit at Newton's second law, and it kind of leads us into this formula, this impulse change in momentum. So I'd like to explore the link and talk about what that means, and it just gives a little bit of a basic rundown of our understanding of momentum. So let's start with some definitions. We know that momentum is the product of an object's mass and its velocity. The units are kilogram meter per second. Of course, if it's the product of mass and velocity, you can see the units being multiplied, and there you go. The formula is there. There's your definition of momentum. I think that's something that you should be, or that you will be familiar with. Okay. Now, something which might be new. If you're at the GCSE level, if you're not doing advanced placement or A-level physics, that sort of thing, IB physics, you might not cover impulse, but impulse is this quantity in which we do the integral of a force over a certain time interval. Now, it doesn't need to be an integral. I mean, that's fine. If we assume it's a constant force, as we will for most of our high school physics, the constant force, if the impulse is simplified to this equation. Okay, there are the units. Okay, note that the units are kilogram meter per second as well, and do a little check for yourself and verify that that's the same thing as saying a Newton second. You'll see why that is. If you look at the formula for impulse, if you were to multiply a constant force, which is going to be exerted for a time interval, that's what the impulse is. So you can see the units being Newton seconds. You can also kind of understand, based on it being equal to the change in momentum, why the units are the kilogram meter per second. Okay, so those are the definitions, just to kind of recap. Maybe you haven't seen that, maybe you have. Okay, and then also before we get into things, let's just have a quick breakdown of the difference between inertia and momentum, because I think people get these confused. Okay, inertia is a property of matter that maintains its state of motion as long as there's no external force acting upon it. So we had said in the first law video that if Newton's first law, if the net force, or the sum of all the forces, is zero and there's no net force, then there's no change into the state of motion. And so that is the inertia. All right. Whereas momentum is the product of mass and velocity. And I think in everyday common, colloquial language, people get these terms kind of mixed up and use them interchangeably, but they actually are quite different, aren't they? Okay. So inertia is just this. It depends. It's the resistance to the change in motion, okay? And it maintains that state of motion, all right? Whereas momentum is the amount of motion that something has. Well, how can that be? Well, momentum is dependent on both mass and velocity. You can have something with a very high momentum. It could be incredibly light, like a particle, like a neutrino, like an electron, but it could be moving incredibly fast. You could also have something incredibly massive, like a glacier, which moves a centimeter per year. Okay, but it's incredibly massive, and it might have more momentum than your rocket car or a jet plane, because the mass is so great. So with momentum, you have to take into account both mass and velocity. Inertia, it only depends on the mass. That is it. Okay, now check out the video on rotational motion for how rotational inertia fits in, with the angular momentum. Okay, but we're just going to deal with linear stuff here for now. And just a quick summary: Newton's first law is the law of inertia. The second law, we're going to talk today about how it leads to the impulse change in momentum formula. And when we get looking, you can check out the third law video and the conservation of momentum video. We'll see how those things are related. Okay, so let's move on. We had said last video that this is your basic underwhelming definition of Newton's second law. We had spoken about how it's probably better to talk about a force being we can express this third law
rate of change
in a mathematical
of
form.
Now I've split it off here as m times delta v.
Well, it's definitely shorter to write down, but easier to understand. You're going to have f, the force
if you want to
A
pretend
acting
m is
on
constant,
B
that's
is
fine.
equal
That's what we
to
had said. We'd
negative
have
the
for
force
most,
of
high
B
school
acting on
situations.
A.
But the thing we're going to do here now is we're going to take this delta t and we're going to just move it from the bottom right and Just swing it up here to the top left. And that's where that delta t comes from, our definition of impulse. Okay, and so you've got a force acting for a certain amount of time, and you've got here mass times a change in velocity. Mass is constant, but this is still going to be the rate of change of momentum. Okay, well, not rate of change, and actually that's an important point to make. This will be the change in momentum. Okay, but here we have the impulse, which is F times delta t, equaling change in momentum. Please don't get these confused. A lot of students do this. The net force is the rate of change of momentum, and I could have written it as delta p over delta t. The net force is the rate of change of momentum, whereas you can here say impulse is equal to the change in momentum. Okay, and this is known as the impulse change in momentum theorem. And this will work for single objects or other particles, doesn't matter what reference frame. So the net force is equal to the rate of change of momentum. The impulse is equal to the change in momentum. And we've gotten the difference by moving that delta t up to multiply by F net. Now we're going to look, we've rearranged this equation, we're going to look at what happens if we've got a certain force, a certain, say you push or you throw or you kick something with a particular constant force. We see there's a proportionality between the contact time, they call it, and the change in momentum. So obviously, the longer that this force is allowed to act upon that ball or that object that you want to push, then the larger the change in momentum will be. And this could be for if you are starting something from rest, or maybe it actually has a negative change in momentum because you wish to slow the object down and you're applying a negative force. That's fine. Okay, direction doesn't really matter. The idea is that the longer the contact time, the greater the change in momentum. So if you want to kick your soccer ball further, then you follow through with your pool shots, with your golf swings, all this sort of thing. And I'm not talking about backswing before you make contact. I'm talking about after you make contact. You have an increased contact time and you have an increased change in momentum. Now similarly, we can look at this slightly differently. This time what we're going to do is we're going to keep the change in momentum constant to catch a ball. What does a cricket player do? What does a baseball player, what does anybody do when they want to catch a ball, something coming at them very quickly? What they'll do is they'll cradle the ball, won't they? Okay? The change in momentum is going to be whatever that object's velocity is multiplied by its mass, and the final velocity we would hope after the catch is going to be 0. So in this case, yeah, you will have a negative change in velocity. That's fine, a negative change in momentum. The idea, though, is that it is a specific constant change in momentum. So what would we do here? Well, if you increase the contact time in this situation, because it's on the same side of the equation as this F net, it means that that value is going to have to decrease. So by increasing your contact time, by cradling the ball when you catch it, by having a crumple zone in your car, by bending your knees when you've jumped, the idea is with a crumple zone or a bicycle helmet crumpling up, it'll increase the contact time, and then you have a lower force being exerted on that object. Now, if it's in the case of a human in a seatbelt or with an airbag, of course that's a less of a force acting on their body, which is what prevents them from getting injured. So you can have a constant change in momentum, which will mean there's an inverse proportionality between the length of time that you are in contact and the force that is felt. All right, or you could have a constant force that's being exerted, and then you can see there's a proportionality between momentum and time. And if I were to go back to the original equation, you see that because the proportionality between the delta p and the delta t is the same, that means that your F net will remain constant. All right. Right, so I hope that has helped some people. I hope that makes a little bit more sense. It's a good way of analyzing Newton's second law, but also kind of introducing to the idea of momentum. So if you've got some other suggestions for some videos, please leave them in the comments. If you've got some questions, please also write them in the comments. Comment, rate, and share. And thanks for watching, and we'll see you next time on 10-Minute Physics.